A structure's main function is to transfer loads. But before considering the form of a structure, a clear idea of what loads it has to transfer is required. In other words, an answer to the question what are the loads. The sources of loads can be divided into natural, useful, and accidental loads. Natural loads occur due to the existence of the structure in the world. Useful loads are ones that occur from the purpose of the structure, and accidental loads occur from the misuse of the structure. Firstly, let us talk about natural loads. All structures on the surface of the Earth have to resist the force of gravity. This force acts through a body in a line joining the body with the center of the Earth. However, at the local level these forces can be considered vertical. So the first source of natural loads is the gravity load. For example, the plank across the stream. This means that the plank has to transfer its own weight, usually called self-weight, to the support points. Due to regular and continuous changes in atmospheric pressure, from place to place on the Earth's surface, air flows across the surface of the Earth, that is, wind. All structures built on the Earth's surface have to resist forces from wind. Near to ground level, the wind can be considered to blow along the surface. This is not true for the whole of the atmosphere, as any pilot knows. If an obstruction is placed in the path of the wind, it alters the pattern of the wind flow. This is why kites and planes fly and boats sail. If the object is fixed to the Earth's surface, like a building, the wind must flow around and over it. How the wind flows around and over an object depends both on the wind speed and the shape of the object. These are the basic questions, considered by the complex subject, known as aerodynamics. But the alteration, in wind flow pattern, will always cause a force on the interrupting object. It is an intellectual feat to see the alteration of the wind flow pattern around and over a building as a force or wind load. But this view allows the action of the wind on a building to be clear. So, for the pitched-roofed building, the alteration in wind flow will cause four loads. The loads W1 and W2 are on, and at right angles to the walls, and the loads W3 and W4 are on, and at right angles to the roof slopes. These are wind loads. As far as buildings, and their supporting structures are concerned, gravity and wind loads are two types of natural loads they always have to resist. There are other natural loads that the structure may have to resist. These are earth or water pressure, earthquakes, temperature, and ground movement. If the local shape of the Earth's surface is altered to site the building, as it often is, then parts of the building and its structure may be subject to loads from earth pressure. This is because the natural surface has found a shape that is at rest, not over geological time of course. So, rather like the wind flow, an alteration will cause forces. If dry sand is piled into a heap, there is a maximum slope for the sides. What is happening inside the heap is complex, and is further complicated by the addition of water, which is why sand castles can be made. If, however, a heap with a vertical side is required, forces are needed to keep the heap in the unnatural shape. This is usually done by building a retaining wall. Because the heap wants to return to a natural shape, the wall must hold back all the sand. This causes loads on the wall. In buildings, this occurs when the building has a basement, or is built into a sloping site. In these cases the structure has to resist natural loads from earth pressure. Under the surface of the Earth, depending on the local geology and climate, there will be, at some level, water. The top level of this water is called the water table. This level may be at the surface in swamps, bogs and beaches, or many meters down in deserts. If the siting of the building interrupts the natural water table, an unnatural water table is created around and under the building. Not only are the walls loaded by the water pressure, but it also causes upward loads on the floor. The building is trying to float. The structure has to resist natural loads due to water pressure. The general shape of the surface of the Earth is the same over the lifespan of most buildings, but may alter slightly due to climatic or geological changes. As the building is attached to the surface of the Earth, local changes will force a change in the shape of the structure, as the building is hardly likely to prevent the Earth changing shape. In particular, load may be caused if the local shape changes differentially. It is not obvious how this causes a load on the structure, if indeed it does. For example, suppose the plank bridge has a support in the stream. If this central support were to sink into the stream bed, depending on the fixing, it may pull the plank down, load it, or cease to be a support at all. So ground movements can alter the load-carrying behavior of a structure, and so can be considered, in a rather roundabout way, to load the structure. Another form of ground movement that can load a structure is an earthquake. Earthquakes are caused by sudden internal movements within the Earth's crust. This causes a shock to the system and results in shaking the crust of the Earth over a certain area. The Earth's surface will both bounce up and down and move backwards and forwards. In general, the vertical movement is small compared with the horizontal movement. A building, during an earthquake, undergoes an experience similar to a person standing unaided on a cakewalk. Again, it is not obvious where or what the load is, but the effect, as far as the building is concerned, is the same as being pushed horizontally to and fro with the foundations kept still. So earthquakes cause horizontal loads similar to some extent to wind loads. The last type of natural load is caused by differential dimensional changes in the structure. All structural materials expand when heated and contract when cooled. As structures are often exposed to the ambient climate, their temperature may vary considerably, from a hot summer day to a cold winter night, and in some cases this may cause loads. An example illustrates how this may happen. Suppose a structure consists of two parts firmly joined by a spanning structure. As the temperature varies, the spanning structure will expand and contract. As it is firmly joined to the supporting structures, it will push them and pull them, causing loads. So, as with ground movements, temperature, in a rather unobvious way, may be a load. To avoid these loads, bridges are often provided with systems of sliding bearings at the tops of the supporting columns. On large bridges these can often be seen. A successful structure must be able to resist the effects of some or all of these natural loads for the whole of its useful life. On the whole, these loads cannot be avoided, and are an integral part of the structure's existence. Useful loads. Unlike natural loads, which cannot be avoided and so must be tolerated, useful loads are ones that are welcome. These loads happen because the building and hence the structure have been constructed for a useful purpose. With the plank bridge, it has been constructed for people to cross the stream. If it couldn't do this, it would be of no use. The amount of useful load can be altered by how many people are allowed on the bridge at any one time, and whether people are allowed to take their pet elephants on the bridge. It is often practical for the useful load to be the maximum load that is likely to occur. Practically, the useful load would be a bridge full of people, but no elephants allowed. So, unlike natural loads, there is a choice for useful loads. Of course, if everyone using the bridge had an elephant or a car, it would be sensible for the useful load to be a bridge full of people or full of elephants. As gravity acts on the people and the elephants, the effect of this useful load will be towards the center of the Earth, or locally vertical. Unlike natural loads, useful loads can vary enormously, depending on the use of the building, which may have to carry anything from railway trains to sleeping people. Whilst the majority of useful loads act vertically, sometimes they act horizontally. It may be useful to store sand, grain or water, and these will cause useful earth or water pressure loads. Also, rather like earthquakes, machinery housed in a building may tend to shake a building sideways, causing another type of useful horizontal load. Again, industrial processes may increase or reduce the ambient temperature, giving useful temperature loads. Accidental loads. The occurrence of accidental loads is inextricably bound up with concepts of safety. How safe anything is, driving a car or drinking water, is a matter for society to decide, or at least keep under review. If accidents are thought to be likely, and unavoidable, then the structure should be able to resist loads that these accidents cause. For instance, in a multi-story car park, it is likely and unavoidable that someone will hit the edge barrier whilst parking. The edge barrier should be able to cater for run-of-the-mill collisions but not suicide attempts. Similar situations occur at railway stations and ship berthing jetties. Another unavoidable accident is a minor explosion. Minor explosions in kitchens and bomb factories are of different orders of magnitude, but both should be expected and allowed for. Other unavoidable accidents are crowd panics which require the installation of panic barriers, or tanks bursting which require lower structures to carry the extra liquid load. It is impossible for an individual to decide which accidents, and hence accidental loads, are unavoidable and which aren't, and any society is never clear about this. Compare the number of people killed on the roads in unavoidable accidents and the relatively few killed in train disasters. Loading summary. The major function of a structure is to transfer loads, and the main sources of these loads have now been identified. Whilst each load or set of loads can be considered to act independently, buildings are usually loaded by combinations of the various loads. As the building must carry any combination, it is usual to consider a range of combinations called load cases. The only load case that will always be present is the natural gravity load. That is the effect of gravity on the building construction, and to this load must be added all other loads. All the other loads that have been identified may or may not be acting at any particular time. Therefore, an almost endless variety of load combinations may act. For example, load case 1. Natural gravity load plus useful gravity load on all floors. Load case 2. Natural gravity load plus wind load in a particular direction. Load case 3. Natural gravity load plus useful gravity load on some floors plus natural temperature load. However, the purpose of considering these different load cases is not to find as many load cases as possible, but to ensure that the building structure will safely carry all possible load cases. This apparently contradictory statement means that only the load cases that cause the biggest effect on the structure need to be considered. In other words, only the worst load case is of interest. This presents two difficulties that are: 1. One load case may cause the biggest effect on one part of the structure, whereas another load case may have the biggest effect on another part, so there may be more than one worst load case. 2. How can the worst load case or cases be found without considering every possible load case? Unfortunately, there is no automatic process to overcome these difficulties for every situation, but guidance is given in technical documents. For buildings, it is usual to consider natural gravity load plus maximum useful gravity load. Natural gravity load plus wind load in direction 1. Natural gravity load plus wind load at right angles to direction 1. It is unusual to have to consider loads due to earth or water pressure, ground movement, temperature or accident. But for particular types of building or sites, these may have to be considered, and incorporated into the load cases. For example, for a two-story factory building, the following loads would be considered for the structural design. The ground floor often bears directly onto the ground and does not load the structure. The natural gravity plus maximum useful gravity loads usually, but not always, give the worst vertical load. The combination of natural gravity load and the maximum wind loads usually gives the worst horizontal load. It may seem surprising that only two directions are chosen for the wind, because, after all, wind blows in any direction. So the maximum wind load, which has been decided, can act in any direction. But if the building structure is strong enough to carry the maximum wind load separately in two perpendicular directions, then all other wind loads can be considered to be smaller proportions of the maximum loads. The same principle of load combinations applies to all buildings. In the same way that people stand on a floor and usually don't fall through, buildings also have to stand on something strong like foundations. But what is the floor doing to stop people from falling through? What it is doing is to provide a reaction force or a reaction load. The idea of reactions is due to Isaac Newton, who in 1687 stated three fundamental laws, which together with his discovery of gravity, provided the basis of what has come to be known as Newtonian mechanics. These were used extensively by scientists in their pursuit of knowledge about the natural world. They formed the backbone of physics and still provide the backbone of structural engineering thought. It was only at the beginning of the 20th century that Albert Einstein postulated a system of mechanics that were non-Newtonian. This system came to be known as relativity, which is used for calculations about the universe. Fortunately, structural engineers can still use Newtonian mechanics for building structures on the Earth. One of Newton's three laws states, "To every action there is always an equal and opposite reaction." So when a person stands on a floor, the weight of the person pushes down on the floor with a force equal to their body weight. For equilibrium, the floor must push back with an equal and opposite force. An understanding of this statement is fundamental for an understanding of how building structures carry loads. Whilst it is true that the load and the reaction have to act at the point of the application of the load, a structure transfers the load to another point. Returning to the example of the plank bridge, the reaction to the person's weight is in the structure, and the structure transfers this reaction to the banks. Because of Newton's law, the numerical sum of the loads and the reactions must be equal. For vertical equilibrium of the two-span beam, P1 plus P2 plus P3 plus P4 equals R1 plus R2 plus R3. When loads are acting horizontally, a reaction is required for equilibrium. It is to upset this equilibrium that tug-of-war contests are held. Here it is unclear which is the load and which is the reaction. This is why the applied load and the reaction load should be thought of as a balanced system of loads. Here the pull of the team is the applied load and the tree provides the reaction load. Not only are there vertical and horizontal reactions, there are also moment reactions. What is a moment? A moment is a force times a distance. Moments abound in structural engineering, but the concept of a moment is often found hard to understand. However, it is because of moments that things can be weighed or people can enjoy seesaws. The fun in seesawing can only be enjoyed if the people are of equal weight and sit at an equal distance from the support. This is because they are in moment equilibrium. In other words, the left-hand person causes an anti-clockwise moment and the right-hand person causes a clockwise moment about the central support. Because both people are of equal weight and are sitting at equal distances from the support, the anti-clockwise and clockwise moments are equal in magnitude but opposite in direction and so are in moment equilibrium. By pushing from the ground, this equilibrium is upset and the people seesaw. The same principle can be used for weighing scales, this time to find the unknown weight of some goods. To balance the scales, the moments must be equal. As the distances are equal, the weights must equal the weight of the goods. The idea of moment reaction occurs at the support of a cantilever. The person sitting on the end of the cantilevered plank causes a moment at the support force times distance. The fixing of the plank must balance this moment with a moment reaction, otherwise the plank will rotate away from the wall. Moment reactions are also required to prevent flagpoles, fences and signs from being blown over by the wind. In this case, the post is acting as a vertical cantilever from the ground. The wind force acting on the sign at some height distance above the ground causes a moment at ground level, so the post must be dug into the ground to provide a moment reaction. Notice that the moment reaction is in the opposite direction to the moment caused by the wind force times height. Many structures require more than one type of reaction. Using the example of wind blowing on a sign, the support must provide vertical, horizontal and moment reactions. These resist the weight of the sign, the wind load and the wind moment. The idea of moment equilibrium also plays a part in apportioning vertical reactions for spanning structures. Suppose a weightless plank spans between two weighing scales and a person stands at different points along the plank. The person is the load and the reaction forces occur at the supports on the weighing scales. As the person moves from position A to B and then to C, the readings on the scales will vary, giving the values of the reactions for each position. But the fact that the sum of the readings on the scales for each position will equal the weight of the person does not indicate how they are shared. If the person stands in position A, directly over the left-hand weighing scale, it is reasonable to expect this scale to give a reading of 100% of the person's weight, and the right-hand weighing scale to give a reading of 0% of the person's weight. But vertical equilibrium would equally be satisfied by the right-hand scale reading 100% of the person's weight, and the left-hand scale reading 0%. This seems unlikely to be true, but why not? The answer is because only 100% at the left-hand scale gives moment equilibrium. But where are the moments? These are far from obvious, but suppose the left-hand weighing scale was removed. Now the person causes an anti-clockwise moment about the right-hand weighing scale and the plank would hinge about the right-hand end. To prevent this, the left-hand weighing scale provides a reaction that causes a clockwise moment about the right-hand weighing scale. As these two moments must balance, the left-hand reaction must balance the person's weight, as the distance from the right-hand end is the same for the load, and the reaction so. Person's weight times length of plank equals left-hand reaction times length of plank, so the left-hand diagram gives vertical and moment equilibrium whereas the right-hand one gives vertical equilibrium but not moment equilibrium. So every time there are loads on structures there must be reactions vertical, horizontal and moment, and these reactions must balance the loads. In other words, sum of vertical loads equals sum of vertical reactions. Sum of horizontal loads equals sum of horizontal reactions. Moments due to loads equals moments due to reactions. These three statements must be true for all structures, and the understanding of these statements unlocks the door to an understanding of structures. To understand how loads are transferred through complex structures, the concept of load path is used. This is basically a sequence of loads and reactions between structural elements. The important point here is one element's reaction to the next element's load. For the simple example of a beam on two walls, the reactions of the beam cause loads on the walls. The double-headed arrow between the beam and the walls represents the reaction and the load. The upper arrow represents the wall providing a reaction to the beam, and the lower arrow represents the beam causing a load on the wall. A more complicated situation of two beams supported by walls, all sitting on a longer beam. First, what are the loads? These are natural, the self-weight of the beams and walls, and useful, the loads applied to the beams. Loads P1, P2 and P5 are the self-weight of the beams, and P3 and P4 the self-weight of the walls. Loads P6, P7 and P8 are the loads applied to the beams. For vertical equilibrium, all the loads P1 to P8 must be balanced by the reactions of the lowest beam. For the lowest beam, the sum of the reactions equals P1 plus P2 plus P3 plus P4 plus P5 plus P6 plus P7 plus P8. But how do the loads get to the reactions? First, the upper beam. Loads to the upper walls equals P1 plus P6. The upper walls are loaded by the loads on the upper beam plus their self-weight. The tops of the lower walls are loaded by and provide a reaction to the upper walls and the middle beam. So for the lower walls and the reactions to the lower walls are load from the upper wall plus load from the middle beam plus self-weight of the lower wall. Reaction equals P1 plus P6 plus P3 plus P2 plus P7 plus P4. The lower beam is not only loaded by its self-weight, P5, and the applied load, P8, but also by providing reactions to the lower walls. So for vertical equilibrium of the lower beam, the reactions equals self-weight of the upper beam plus self-weight of the middle beam plus self-weight of the lower beam plus self-weight of the upper walls plus self-weight of the lower walls plus useful load on the upper beam plus useful load on the middle beam plus useful load on the lower beam, which is R1 plus R2 equals P1 plus P2 plus P3 plus P4 plus P5 plus P6 plus P7 plus P8. The load path of load P6 can now be identified. First, the upper beam transfers the load to the upper wall, which transfers it to the lower wall, which transfers it to the lower beam, which transfers it to the supports. And for P2, the self-weight of the middle beam, the load path joins the load from its point of application to the final support point. There are two facts to be considered about load paths. Firstly, all loads must and will have a load path from their point of application to the final support. The structural designer must identify these paths for all loads and all load cases. Secondly, as the function of the structure is to transfer loads, then the load path is the structure for each load. So the answer to the question "what is the structure?" may vary with each load. For the loads P2 and P6, the structures are different. The identification of vertical load paths for most buildings is relatively straightforward. Oddly, it can be quite complex for simple buildings, like houses. Not only do vertical loads need load paths, but so do horizontal loads. These loads are usually caused by wind. How does the signboard resist wind forces? The main wind load is caused by the wind blowing on the actual sign, and only the load path for this load is considered. This means the effect of the wind on the rails and posts is ignored. The actual signboard spans horizontally between the vertical stiffeners, and the stiffeners act as vertically spanning beams, supported by the top and bottom rails. The reactions from the stiffeners become horizontal loads on the top and bottom rails. These rails act as horizontally spanning beams, supported by the vertical end posts. The reactions from the top and bottom rails now cause loads on the vertical posts that act as vertical cantilevers from the ground. For the signboard, the wind load path is the whole structure. But even in simple buildings, the load paths for vertical and horizontal loads are rarely the same. As the load path is the structure, this means there are usually different structures resisting vertical and horizontal loads. Thanks for watching. We hope you found some useful tips. Check out our website at structuralengineercalcs.com. Please like and subscribe, and let us know what would you like to see next. The human footprint is a masterpiece of engineering and a work of art. Stay safe. Goodbye, and see you soon.